Hello students, I am Dr. Ritu Agarwal from Department of Electronics and Communication Engineering. Today I would be discussing encoder and decoder, which is the part of combination circuit, and it is in continuation with the lecture series of digital system design. So first of all, we will start with the encoder part. Encoder is a combination circuit that converts binary information in the form of 2 to the power n input lines into n output lines, which represent n bit code for the input. For simple encoders, it is assumed that only one input line is active at a time. So to explain the encoder in more detail, we would be discussing octal to binary encoder. In octal stands for 8, while binary stands for 3. So we will be having 2 to the power 3 inputs, that is 8 number of inputs, and 3 outputs in the form of binary. So we will start with the octal to binary encoder truth table. So the truth table will be having 8 inputs, that is D0, D1, D2, D3, D4, D5, D6, and D7. And the outputs will be X, Y, and Z. And since we are having 2 to the power 3 inputs, that is equal to 8. So we are having 8 number of inputs and 3 number of outputs. So these D0 to D7 are the inputs, while X, Y, Z are the outputs. So for D0, in first case, we will have D0 equal to 1 and rest all will be 0. Now corresponding to this, obviously D0 is 0, so we would be having the binary as 0, 0, 0. Then in the next case, we have 0. Then D1 is 1. Then we would be having 0, 0, 0, 0, and 0. For the case of D7 also. Then for XYZ, we have 0, 0, 1, which is the binary equivalent of 1. Then for 0, 0, 1, that is D2 is 1. In this case, the binary equivalent of decimal 2 is 0, 1, 0. Then for the third case, we have D3 as 1, and the decimal equivalent of D3 is 0, 1, 1. Then in the next case, D4 will be 1. And therefore, the decimal equivalent will be 1, 0. For the next case, D5 will be 0, 1. And the output is 1, 0, 1. Then we have D6 as 1. And therefore, the output will be 1, 1, 0. And for the last case, D7 will be 1. And therefore, the output will be 1, 1, and 1. And therefore, the value of X will be equal to D4 plus D5 plus D6 plus D7. Then in case of Y, it is equal to D2 plus D3 plus D6 plus D7. Then Z will be equal to D1 plus D3 plus D5 plus D7. So these will be the output expression for X, Y, and Z. And now we can plot, or we can draw the circuit diagram or the logic diagram with the help of these X, Y, Z outputs. So here we can see the outputs, that is x is equal to d4 plus d5 plus d6 plus d7, y equal to d2 plus d3 plus d6 plus d7, and z is equal to d1 plus d3 plus d5 plus d7. Now based on this, we can draw the logic diagram. So this is the logic diagram. In this logic diagram, we can see the values of x, y, and z, which we have already derived with the help of this truth table. That is x, y, and z. X is equal to d4 plus d5 plus d6 plus d7. Y is equal to d2 plus d3 plus d6 plus d7. And z is equal to d1 plus d3 plus d5 plus d7. So here we have used an OR gate. In OR gate, d4, d5, d6, and d7 are connected. For the next OR gate, for y, D2, D3, D6 and D7 are connected, and for Z, D1, D3 and D5 and D7 are connected. So with this, we can draw the logic diagram of an encoder, which is an octal to binary encoder. But this octal to binary encoder or any kind of simple encoder has some limitations. So in the next slide, we would be discussing those limitations of this encoder. So what are the different limitations of this encoder? Only one input can be active at any given time. If more than one inputs are active, then the output is undefined. For example, if D6 and D3 are active, then our output would be 1, 1, 1. How it can be 1, 1, 1? If D6 is 1, then obviously X will be 1. And D3 is 1, then Y will also be 1. And if D6 and D3 are 1, then Z is also 1. So X, Y, Z, all the three are 1, 1, 1. And therefore, it will represent the output for D7 instead of D6 and D3. And we want the output for either for D6 or for D3. So this will be giving the wrong output. So to overcome this problem, we use the priority encoders. And another problem arises when all the inputs are 0. We have seen that when D naught is 1, then the output is 0, 0, 0. But if the input is 0, 0, 0 or all the inputs are 0, then also it will give us the output as 0, 0, 0, which actually is the output for D naught. Therefore, to avoid this, an extra bit can be added to the output, and this is called the valid input, valid bit or the valid input, which is 0 when all the inputs are 0 and 1 otherwise. So to overcome these problems, these two problems, that is the problem of all the zeros and the problem of when more than one input are 1 or when more than one inputs are active. And to overcome this problem, we would be using priority encoders. Now we would come to the next topic, that is priority encoder. Now, what is a priority encoder? A priority encoder is an encoder circuit in which inputs are given priorities. When more than one inputs are active, at the same time, the input with the higher priority takes precedence and the output corresponding to that is generated. So, अगर हमारे पास एक इनपुट से ज्यादा है एक्टिव एक बार एक साथ, तो हम प्रायोरिटी किसको देंगे? जिसकी प्रायोरिटी ज्यादा होगी उसको हम एज एन इनपुट रिप्रेजेंट करेंगे, और जिसकी प्रायोरिटी कम होगी, जैसे हमने प्रीवियस एग्जांपल में देखा D3 एंड D6, तो वी वुड बी गिविंग मोर प्रायोरिटी टू D6 एज कंपेयर टू D3. सो हाउ वी कैन डिजाइन दिस सर्किट? So a priority encoder is an encoder circuit in which the inputs are given priorities. When more than one inputs are active at the same time, the input with higher priority takes precedence and the output corresponding to that is generated. So we will be seeing how the priority encoder is used and how the higher input is given priority. Priority encoder can be of two types. It can be in which we can give the priority to the higher input, or we can give the priority to the lower input. So in this case, we would be taking priority to the higher input. So for that, we would be drawing a logic diagram, truth table. So in this truth table, we have 4 inputs, that is D0, D1, D2, D3, and three outputs, that is X, Y, and V, where V stands for the valid input. If all the inputs are 0, that is D0, D1, D2 and D3, all the inputs are 0, then X and Y will be 0, 0, or we can say X and Y will be don't care. So either we can write 0, 0, or we can write don't care for X and Y, and for valid input will be 0 in this case. So here, instead of writing 0, 0, we can also write the don't care. X and Y are don't care, and the valid input is 0. While in case of D0 is 1, then in this case, D1, D2 and D3 are 0, 0, 0. In this case, X and Y will be 0, 0, and the valid bit will be 1. Then for D1 equal to 1, the X and Y value will be 0 and 1, and the valid bit will be again be 1. Then for this case, in this case, instead of writing 0, when D1 is 1, we will have to write don't care instead of 0. Why we will have to write don't care? Because we have to give the priority to D1 instead of giving the priority to D0. So here we can erase this 0. And in this case also, we can erase this X and Y 0, 0. We can have only don't care. So in another case, is when D2 is 1. So when D2 is 1 and D3 is 0. In this case, D0 and D1 has to be don't care. So we would be giving priority to D2 instead of D0 and D1, and D3 will again be 0. And X and Y will be, in this case, will be 1, 0, and valid bit will again be 1. Then the last case is D0, D1, D2 will be don't care, and D3 is 1, while X and Y will be 1, 1, and the valid bit will also be 1. Now, based on this truth table, we can draw the K-maps. For the X, we would be having 3 K-maps for X, Y, and V. For X, we are having the K-map as, it would be a 4-variable K-map. So, in this case of 4-variable K-map, the inputs will be so this is a 4-variable K-map. In this case, inputs will be D0, D1, D2, D3, and output, this is for X. And since it is for X, 1 will be at these places. Means we have for all zeros, we have the don't care. This is the don't care condition. For 0, 0, 0, 1, 1, 1, and 1, 0. Here also we have 0, 0, 0, 1, 1, 1, and 1, 0. So for the first case, that is when all are 0, then X is don't care. Then we have 1, or then 3 zeros. Then we have again 0, that is 1, 1, then 0, 0, we have 0. Then the next case is 0, 1, 0, 0. So this is 0, 1, 0, 0, we have 0. And another possibility of this case can be 1, 1, 0, 0. That is 1, 1, 0, 0. And rest, at all the rest places, we would be having 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1, 1. So we can have the group, 2 groups over here. One group is this one, and another group will be the next group of we can have another group. This another group will be D naught. So this first group will give us the output as D2, sorry, D3, and second group will be giving us D2. So X will be equal to D2 plus D3. So this is the next group. So X will be equal to D2 plus D3. Similarly, we can draw the K-map for Y and V. So for Y, K-map will be this would be the K-map. Again, a 4-variable K-map. So in this 4-variable K-map, the inputs will again be D0, D1, D2, and D3. And the output will be at, it is don't care for 0, 0, 0, as it was in the previous case. Then it would be 1 at so in this case, when D0, D0, D1, D2, and D3, for don't care 100, we have 1. It means we have 0 at 2 places, 100. That is, here we have 00, 01, 11, 10, and here also we have 00, 01, 11, and 10. So for here we would be having for all the zeros we have don't care. Then for 100, the value of Y is 100, the value of Y is 0. Then for don't care 100, the value is 1. So don't care 100 is 0100, that is 0100, and 1100. So at these two places we have 1, 1. And in the last case, that is don't care, don't care, don't care 1, we have 1. So at these places, that is 0001, 0001 will be this place. Then we have all these places, that is 1, 1, 1. Then again we have 1, 1, 1, and 1. So here in this case also, we would be having two groups. So this is the first group. And this one is the second group, that is a group, that is a quad. So in this case, Y will be equal to, for the first case, we have D1 and D2 bar plus D3. So this is the case for Y. And for V, we have 0 at only one place, and at rest all the places we have 1, 1, 1. So this will come out to be D naught plus D1 plus D2 plus D3. So these are the three expressions for priority encoder. That is D1, D2 bar plus D3. For X, D2 plus D3. And for V, D0 plus D1 plus D2 plus D3. So with the help of this, we can find the value of priority encoder and we can draw the logic diagram. So we can draw the logic diagram with the help of this X, Y, and V. So first of all, we will start with the X. Now, what is the value of X and Y and V? So for the case of X, we have D2 plus D3. And since we are having D2 plus D3, so we have an OR gate with the inputs D2 and D3. So this will give us D2 and D3. Output is X. For Y, we have from the previous slide, we can see for Y, we have D1 plus D2, D1, D2 bar plus D3. So we have an AND gate also in which we will give input at D1. D2 bar will be given by with the help of a NOT gate. So from here we are getting D1, D2 bar, where we have D1. Here we have input as the D2 plus D3. So we have this D3. We can even connect the D3 from the same input as we have given for the X, and this is for Y. For V, we would be having all the four inputs, that is D0 plus D2, D0 plus D2, D1 plus D2, and plus D3. So all the four inputs are here. That is D0, D1, D2, and D3. So with the help of this, we can find out the priority encoder in which we have a valid input and X and Y are the outputs in which the higher bits are given priority instead of giving the priority to the lower one. We can even design the priority encoder for the lower one also. So in case of lower one, we will have to give the priority to the lower bit. That is, if we are having two bits, D2 and D3 as active, then priority will be given to D2 instead of D3. While in this case, when we are drawing a higher priority encoder, we are giving the priority to D3 instead of D2, as D3 would be high as compared to D2. So this is all about our priority encoder. Now we come to another topic, that is decoder. So decoder does just the opposite of an encoder. It is a combination circuit that converts n lines of input to 2 to the power n output lines. Means if we are having n number of input lines, then we would be having 2 to the power n output lines. So in case of this, we can have 2:4 line decoder, we can have 3:8 line decoder, we can have 4:16 line decoder. So if the value of n is 2, then the output will be 2 to the power n, that is equal to 2 to the power 2, that is equal to 4. Means 2:4 line encoder. Oh, sorry, decoder. Now, secondly, we have, if we have n is equal to 3, then we can have 2 to the power 3, that is equal to 8, which is 3:8 line decoder. We can also have n is equal to 4, in which we have 2 to the power 4, that is 16. So we would be having 4:16 line decoder. So first of all, we would be discussing 2:4 line decoder. So in case of 2:4 line decoder, we have two inputs, that is X and Y, and corresponding to this, we would be having four outputs. So we have 2:4 line decoder. So in case of 2:4 line decoder, inputs will be 0, 0, 0, 1, 1, 0, and 1, 1. So now what will be the outputs? Outputs can be D0, D1, D2, D3. So we have 1 for D0. All the outputs will be 0. And since we are having 0, 1, so we'll be having 0, 1, 0, 0. Then for 0, 0, 1, 0. And lastly, we have 1, 1. So we will be having 0, 0, 0, 1. So in this case, we can write the outputs as D0, D1, D2, and D3. So here D0 will be equal to X bar, Y bar. D1 will be equal to X bar, Y. D2 will be equal to X, Y bar. And D3 will be equal to X, Y. So with the help of this, we can draw the circuit of decoder. So here we can see that decoder has 2:4 line decoder. 2:4 line decoder. We have 4 output lines and 2 input lines. For 4 output lines, we have D0 equal to X bar Y bar, D1 equal to X bar Y, D2 equal to X Y bar, and D3 equal to XY. So with the help of this, we can find out the logic diagram of this circuit. So the logic diagram can be drawn with the help of D0, D1, D2, and D3. So we have for D0, we have X and Y, 2 inputs are there. X and Y, 2 inputs are there. For D0, for the first input D0, it is connected to X bar and Y bar. So this will be connected to a NOT gate. Then Y will also be connected to a NOT gate. So we have the option D0 equal to X bar, Y bar, D1 equal to X bar and Y. So this is again connected to AND gate. And from here we will get the output as D1, which is equal to X bar, Y. Then we have X and Y bar. So the output is D2, which is equal to X, Y bar. And for D3, we have X and Y. So D3 will be equal to X and Y. So this is the logic diagram for 2:4 line decoder. Similarly, we can draw the circuit or the logic diagram for 3:8 line decoder. So we can have n number of lines and 2 to the power n number of outputs. So this is all about our encoder and decoder. In the next lecture, we would be covering magnitude comparator. So till then, have a nice day. These are the references. Thank you.